Very much, Dr. Moreo. Hello, good morning, everyone. I am Rafael Cardona, and it's my pleasure to be presenting here today. Thank you, all of you. Thank you to the Smile Up team, and thank you to Dr. Moreo for inviting me today. Also, I see that I have some of my colleagues from New Mexico, so hello, everyone, and I hope that you are doing great. Today, I'm going to be presenting the work that we carried out during the first semester of the last year at the Smile Lab with the support of the University of New Mexico and also with the support of the School of Engineering of Ciudad Real. It was the school where I was doing my master's. So we counted with the help of my advisors, my previous advisors at the time, that were Dr. Moreo and Dr. Lozano, and thank you very much to both of them. We also performed this research with Xinxin Yuan, a PhD student at the UNN, and Feiyu Gu. And that's it. And the work consisted on the monitorization of the Sandia Peak aerial tramway that is located on the city of Albuquerque. Okay. So I'm gonna start telling you about the structure of the presentation. In this presentation, we have little time, so I'm going to be focusing on the last part of the research, that was the field deploy on the structure and the analysis of the results. But we don't have that much time to talk about the previous work that we did to this final step of monitoring the structure. So for the presentation, I'm going to be introducing what's the Sandia Peak Tramway, what was the objective of the research, what was our idea, and what was our intention with this work, and also how we did the field deployment. In the end, I'm gonna pass very fast through the characteristics of the sensor that we designed, because we don't have that time to talk about all the design and testing process for the new sensor that we developed. And we will finish showing the results and the conclusions that we got. So the Sandia Peak Tramway goes from the base of the Sandia Mountains in the northeast of Albuquerque to its top. The Sandia Mountains area is a wonderful natural environment included within the limits of the city of a national park, the Cibola National Park. You know, it's just a marvelous area right in the city limit of Albuquerque, so it's very close to all the citizens of Albuquerque. From the top base of the tramway, you can access a viewpoint. You have multiple hiking trails and even a ski resort. So people not only use the tramway as an attraction, but it's also a way of transportation. Instead, some people use it instead of driving by the road on the other side of the mountain. So, and the tramway is saving a lot of time to get to the top of the mountains. The tramway was opened in the 1966, so it means that it's been open for 54 years. I want to leave you here the link of the webpage of the Sandia Peak Tramway. There's a lot of pictures, there's a lot of videos there, and there's also very interesting information about the history of the tramway and the construction process of the tramway, that it's pretty curious. So everyone who is interested, I leave here the link. I invite you to take a look at it if you're interested. So that was the structure where we perform our research, and what was the objective of the research. Okay, so what we wanted was to develop a technology that somehow were useful to assist the staff that is operating the tramway. So we wanted to help the operators to monitor the traffic operations of the tramway. Currently, the tramway lacks much automatization, so most of the control and the data that is recorded manually. Because of that, what we wanted is to develop some technology that would be easily applicable, and the wireless smart sensor were a very good option for that. We wanted to measure the acceleration, and we wanted to see what information we can get with that data, what information we could get about the traffic operation of the tramway. So in this slide, you have also a longitudinal profile of the tramway for you to better understand how this structure works. So we have a lower base at 2,000 meters and an upper base at an elevation of 3,128 meters. So the cars, the tramway climbs from the lower base to the top, 1,128 meters. It climbs through 4.7 kilometers. It counts with 2 towers. We are going to place the sensor in one of them, and also we are going to place a second sensor on one of the cars. Now for the field deploy, what we did is placing the sensors. You can see here the day of the installation of the sensors, that this is the sensor that we put on the car. We counted here with the help of the maintenance team of the Tramway, so thank you very much to them for this help. And also we installed our first sensors on the top of the Tramway, on the top of the Tramway car, and it was easy to install since we fixed some magnets to the solar panel and to the sensor. So we wanted to make the work a little bit easier for the maintenance team. This one is this picture is from the sensor that was installed on the tower. This sensor was installed on the first tower, the one that was lower, and we wanted to install it on the beam that supports the cable. You can see in the picture that we wanted to install the sensor on the tip of the beam, and also the solar panel was placed on a location that took most of the daylight, most of the sunlight that it could, so it was able to power the sensor for a longer time. Okay, now this is the sensor that we developed and that we installed on the Tramway. This is the last one of the Lewis 4 series, I believe, unless there is a new one since I left the SmileUp. We don't have the time to talk about the details of the sensor, so very fast what I can say is that it has it is solar powered. It has a battery and a solar panel, so the solar panel charges the battery and the battery supplies the sensor during the night. With this sensor, we were able to record for 4 days on the Tramway, continuously, non-stop. So it was a good adaptation that allowed us to record for a long time, to record for days. Because generally, when we have sensors with batteries, we can only record data for a few hours. We have also to adapt the software to adapt it to a long-term measure. After all that, it worked out, so it was good. And now for the field deploy, these are the locations where we installed the sensors. You can see that this one was installed on the tower, on the first tower, on the right side, looking from below. And the second sensor was installed on the blue car, on the car that was on the left side. And this is the first sensor that we installed on the car. So now to talk about the results. Here what we have is a snipping of the data showing only one of the multiple flights that we recorded over the 4 days. Here what we are showing is information of the acceleration in the vertical axis of the tower and the vertical axis of the car. So the graph on the top shows the data collected from the tower, and the one down shows the data collected from the car. The information of the 2 graphs can be compared for a better analysis. That's why we wanted to place the 2 sensors on different locations. And well, on the data, on this data, we can find interesting events that are marked here, and that provides interesting information about what we wanted to know about the operation of the Tramway. The first event shows the car that didn't have a sensor. In this case, is the red car, and the event 1, what it shows is the car passing through the first tower. It's interesting to find how the average acceleration on the tower is higher or lower depending on where the car is on the cable. So, for example, while there is a car on the part between the lower base and the first tower, the average acceleration is higher. And this happens also on the event number 4. So that when the blue car passes through tower 1 and heads to the lower base, we have a higher average acceleration after the event 4. This is kind of the information regarding the operation that we wanted to find and we expected to find. Now the event 2, as you can see in the graph, we have a peak. So this peak means that the red car on the longitudinal profile is passing through the tower number 2. It's interesting to find how the average acceleration decreases way more than when it passes through tower 1, and this means this is because the velocity of the car is much lower when it passes through tower 2 than when it passes through tower 1. So again, this is some information about the operation of the tramway that it's pretty interesting, and also the peaks that we can find in event 2 and we can also find in event 3. These higher peaks, what shows are the reduction of the speed of the cable, and there's like an impact on the tower when the cable breaks. So, and that happens also on the event 3. Now the event 3 is the blue car. The blue car is the one who has that has the sensor. The event 3 shows its space by the tower number 2. You can find also that in the car data, the acceleration doesn't show that much difference when is the red car the one that is passing, or when it's the blue car the one that passes. So event 2 and 3, the decrease in acceleration is similar. This means that the difference on acceleration is given more by the speed, by the reduction of the speed of the cable, rather than by the car passing through the tower. And now in event 4, what we have is the blue car with the sensor passing through the first tower. We can see on the car data a reduction of speed. We don't find that much acceleration on the tower data. So these are the results that we got, and what is interesting to find is that with two sensors and with two sensors measuring acceleration, we could find interesting information about the operation of the tramway. We could find information related to the speed, and we can find information related to the location. We showed only one flight, but this pattern repeats on all the flights that we recorded over the 4 days. And the data from the car can be compared with the data from the tower, so we can correlate and get conclusions from both of them. Also, one really interesting conclusion is that researchers expected that most of the acceleration were given by the impact of the car passing through the tower, and it's not been like that. Most of the acceleration recorded on the tower is given by the velocity of the cable passing through the tower, and the accelerations recorded on the car comes given by the velocity of the car instead of the impact when it passes through the tower. And general conclusions about the research is that we were able to implement wireless smart sensor to find information, to get information that assists operators with traffic monitoring tasks. That information on speed, time, and position can be obtained from that acceleration data that we recorded. Also, the lowest force sensor that we designed by ourselves was validated and was tested properly. What I was saying, that the highest vibration of the tower are given by the friction of the cable and not by the load of the car passing through the tower. Now, after this research, and in my opinion, I think that we should focus further research on mostly on the data management and analysis, because if we are going to be recording over days without stopping, we're going to have a lot of data. And when researchers find that huge amount of data, it's difficult to process. So you have to look for good techniques and advanced techniques to process big data. Also, wireless communication, the sensor must be synchronized and they have to communicate to each other in a network. Also, synchronizing the sensors as a network is difficult, and there has to be some more research on that. So thank you all of you for your attention. Thank you for inviting me today to present the work. And thank you everyone who funded this project, from SmileLab, from the University of New Mexico, from the University of Ciudad Real, from the School of Civil Engineering of Ciudad Real. Thank you.
Thank you so much. We have some time here for questions, so why don't we go ahead and read the chat. Rafa, can you read the chat now?
Yeah, let me check.
So one of the questions was how long to monitor the Tramway, and in which case do you need to monitor the Tramway?
Well, we want to monitor the Tramway always, because it's if we want to put the sensors for very long time and we want to assist operators on their daily works, it's going to have to be always working to provide that assistance at the same time that the Tramway is working. And what was the other question? For how long we want to leave them working?
Yes.
Yeah, ideally the sensor, as I say, should be working at the same time that the operators are working the Tramway and that the public is riding the tramways, because it would be an assistance tool. For this research, we were recording for 4 days, but this was a research. This was not the final implementation of the Tramway that someday can be done.
Thank you. The other question also is about the size of the data. How many gigabytes are you collecting each day?
So I don't remember how many gigabytes we were collecting, but I remember that we were recording at 250 hertz. So that was a huge amount of data that we could not process with Excel. We have to go with big data because the Excel was taking too long to process. So it was really difficult to manage it with MATLAB also. And the only solution was to snip the data and divide it in many different files. That's why I think that further research has to be done on how to process that huge amount of data.
Thank you very, very much. Any other question before we move to the next speaker? You can chat or you can speak. Sounds good. So then we'll move to the next speaker. Thank you, Rafa.
Okay, thank you very much
for joining us from Spain today, and good luck in your next step. And come to the Tramway frequently.
Of course. Thank you, Dr. Moreno. Bye-bye.